the fourth module for basic hydrodynamics. So, we will cover some examples. So, I will take some vector fields. So, in fact, there are simple examples, no complicated pipes, channels and so on, just simple velocity field, it will compute energy, vorticity and so on. So, this is a velocity field. So, x hat means x component and this y hat means y component, and I given you is functional dependence. So, ux is sin x cos y and uy is cos x sin y. Now, this is a very important velocity field, at least for me. So, there are some interesting properties. So, we are going to do it for a box. So, let me also say this, I am going to do for this is a 2D field. So, pi by pi box. So, box size is pi pi. So, let me first show you the vector field. So, we can plot the vector field, you can easily do this in Python. Okay. So, this will be some exercises you will be asked to do. So, is the arrows visible? So, this velocity field is going like that. Okay. You can see is like that. Now, at x equal to 0, at x equal to 0, this is x equal to 0 line. Now, sin x is 0. So, the first term is 0 altogether. It has only ui component, and ui component is, in fact, it varies. Cos x is 1, this is 1 at x equal to 0, it varies as sin y. If I can see that velocity is uy sin, so negative sign, no, so it is negative sign. So, it is always 0 to pi is negative, is negative here, is going like this. It is a steady flow, it does not change with time. Now, one important point is that the ux is 0 at these two walls, x equal to x equal to pi, but ui is not 0 at these walls, the wall with the red line, this wall. So, this is not, in fact, it is not true for rigid walls. Rigid wall, I said the velocity, both the components must be 0. So, this wall has this peculiarity that the velocity is not 0, the tangential component is not 0 at the wall, and this is called free slip basis. Okay. This is free slip basis. So, my perpendicular component toward the wall is 0, but the horizontal or tangential component is not 0. Same thing here, for here ui is 0, in this walls ui is 0, ui is vertical for them because is y direction, no, this is y, this is x axis, this is y axis, and here ux is 0. But you can easily see for this wall, for the vertical walls, partial ui partial x is 0. So, if I take this ui, this one, if I take derivative with x, what will I get? Sin x, that becomes 0. So, this is called stress free. So, stress is, if you know fluid mechanics, well, stress is proportional to tangential derivative. So, say this velocity field, how does it change in that direction? If the velocity does not change perpendicular to the wall, then it is called stress free. So, there is no stress. Stress when it comes, when your partner is not going along with the same velocity, that is stress. There is a race, people are not running together, then there will be stress. So, here if they move with the same velocity, then there is no stress. So, in fact, you see that this ui are roughly, you can see, well, it is not very visible, but ui are approximately equal near the wall. So, stress is 0 at the wall, that is called stress free. Okay. Yeah.
We will be evaluating the stress after.
So, given the velocity field, I can compute stress. Okay. Now, this is not, I am not solving for you from the Navier-Stokes equation, I am just giving the field and we will analyze few properties. So, this wall has, in fact, u perpendicular is 0 and u parallel un, n is normal, okay, this 0. So, this is called stress free. Now, I can show that the divergence of this is also 0. So, let us compute the divergence. So, first term, if, so what is divergence by the way? So, I am going to write it here, del dot u is partial x ux plus partial y ui. So, when I take the derivative of this with regard to x, will I get cos x cos y, right? sin x becomes cos y. So, first term will give you cos x cos y. What about second term? Cos x cos y, right, because sin y becomes cos. So, cos x cos y. So, that is why I have it here is 0. So, it is divergence free. In fact, it is nice for a lot of calculations, is d free and is very easy to write. It is stress free and is nice circulation. In fact, in convection we get nice this convection role, you know. So, we use this as an interesting basis function or basic mode for representing thermal convection. What about vorticity? Does it have vorticity? Can you make a guess it has vorticity? It looks like there is some cyclone, no? There is a hurricane. So, you can compute vorticity. Yes, indeed. So, I will leave this as an exercise, okay. I will not do this, but you can just do that this partial x for uy is 2D. So, you do not need to compute all the 3 components, just compute this one and it is 8a sin x sin y. 0? No. So, uy, if I take the derivative of this with x, we will get minus cos x, cos will give you plus sin x here, and if I take derivative of this, so that with y will be minus. So, minus minus becomes plus. So, minus minus becomes plus. So, minus minus becomes plus. So, it is 8a sin x. Okay. So, both give you plus contribution. Minus minus becomes plus. Okay. There is a, if I take, well, it's if I take dy I will get this minus sin y and there is a minus sign again and it becomes plus. Okay. So, it is non-zero. You can see there is a hurricane. Now, vorticity is 0. What about energy? How do you compute kinetic energy? U squared by 2. Now, I want to compute the average energy. So, this is important quantity which we want to compute average, because if I make a bigger box then my energy will be more. No? So, in my notes at least I kind of say, well, let us compute average kinetic energy, means energy by volume. Now, it will be area, it is 2D, so it is area. So, let us do one of the terms. So, sin x cos y, square it. So, the first term I am going to do, so 16a squared by 2, I am doing ux squared, I am doing ux squared. So, this is ux squared average, 16a squared sin square x cos square y average. They are independent, no, x and y, no coupling. So, it can be written as sin square x cos square y. And what is the average of sin square x? 8a squared. What is the average of sin square x? Half. So, half, and cos square y also is half. You can do over a periodic box, average is half. So, that gives you 2a squared. So, ux squared is 2a squared, uy squared is also 2a squared. So, total is 4a squared. Okay. So, that is kinetic energy. Helicity is 0, right, u dot omega is 0, no problem. Whether this is omega z, so this is omega z. You can also compute entropy, E omega. Now, this I will again ask you to do it. So, you need to compute a square of this by 2. Okay. So, you can easily do it. It is non-zero. This entropy is a 2D system, is entropy. So, the example 1 is a free slip, is nice convection roll, nice roll sitting there, and we will use it in future. Okay. So, my examples will be like this. So, in this course we will consider this kind of examples. We will work this in Fourier space, we will put some more modes, you know, this is only single mode. I will discuss the Fourier space, then you will say that, well, this is basically one Fourier mode. Example 2. So, my velocity field is this, minus 2x sin y and plus 2y sin x. In a box is, I made it a bigger box, 2 pi box, 2 pi by 2 pi box, 2D is periodic with periodicity 2 pi. Now, we can again compute the same stuff. So, this is standard exercise. So, well, before I do, so string function, okay, this string function is useful. So you can compute string function, and the definition of this size string function. So you can compute ux in ui given string function, or I can compute psi given ux in ui. Okay, this is simple mathematics, and you should be able to do it. I can compute psi. Okay, so this I will leave it this part. Fine or not fine? Okay, so compute psi is 2 cos x plus 2 cos y. You can also compute vorticity. So vorticity is partial, so that partial x ui minus partial y ux, it is this. So vorticity is along z direction, it is 2 cos x plus cos y. Of course, omega and u are perpendicular because omega is along z direction. You can compute kinetic energy. So please make sure that it is ux squared plus ui squared. Okay, so u squared is sum of 2 for 2D and sum of 3 quantities in 3D, u square plus ui square plus uz square. Now what instead of it is 2D, so it's only one omega, this omega z, so it's 2. How does this flow look like? It's an interesting flow. So I will show you the picture. So this picture, I mean, in our Python course in the past you have done it. So please use those scripts to make these plots. Kinetic velocity is 0 naturally because omega and. So this is the picture of the velocity field. It's not coming out very well, but you can see that it is going in that direction. It's clockwise. Now here it is anti-clockwise, like that. Here it is, by the way, it is the same, is periodic. So this guy here is repeated here. So there is a pattern here. This is counterclockwise. So this is cyclone. This is anti-cyclone. What about this? This is again, in fact, this is periodic, so it should be here. Cyclone. This is also, so in fact that 4 cyclones here and 1 anticyclone. But what about, I mean, this looks asymmetric, no, the 4 cyclones and 1 anticyclone. So it should be periodic. So where are other anticyclones? Is periodic. So there is anticyclone sitting here, here. There is anticyclone sitting here, the anticyclone sitting here. So there is one cyclone in the middle and 4 anticyclones around. So the, in fact, is a periodic lattice of cyclones and anticyclones. So cyclone sitting in between 4 anticyclones and 1 anticyclone sitting in between 4 cyclones. Okay. So this is nice example for rotating flows, or even 2D. This is what we tend towards. Now since I already computed string function, in fact I am more interested in well, right now string function, but I will show you later. So the anticyclone in the middle, I should say, not everywhere, in the middle, okay, is at pi pi, okay, this place in the middle, its coordinate is pi pi. Now we can also compute, so this is my string function, okay, and omega z in string function are the same functions which is there in the left slide before. So omega z and string function have very similar property, that it is here, it is positive, omega z is positive, no, here you see, this is positive and it is negative here. So I defined in the last slide. So you can see that ux is d psi dy with plus sign, no, and ui is minus d psi dx. So string function is by definition contours with constant. The velocity field is tangential to the streamlines. Okay. So velocity field is, so if you just join all the lines. So basically, yeah, you just draw the lines and velocity field is tangential to the streamline. Okay, it is useful for a lot of applications, but if you don't really understand it or not fully.
If we find any scalar potential associated with U, that
No. Scalar, that scalar is different. So stream function has a very specific meaning. It has to satisfy this property.
so psi is here.
Stream function, psi is stream function, not potential function.
Okay.
Okay. So you can see that it is negative vorticity, a positive vorticity here, this dark area, density plot. Huh? So dark he is positive because this is cyclone, and in between is bright white. So it is anticyclone. Anticyclone is, sorry, clockwise. This clockwise, no, this clockwise. So minus, plus, plus, plus. This sign of omega z. And this is an example where we have cyclones but no helicity. There is no kinetic helicity, 0. Okay. So example 3. This is helicity. Okay. So in fact this ux and uy are exactly same, but I am putting uz. So this has this in the middle anticyclone, but now this is a vertical velocity. So this is a chance of having u dot omega is non-zero. Now for this you can compute omega. Now I think I have space for doing it, but I will not do it. You can just do this algebra, and you will find that omega is equal to u. The example is chosen in such a way, omega is equal to u. So shall I leave this as an exercise for you? Just compute, and omega is equal to u. And picture I am going to show you, I think is in the next slide. So Hk is positive, kinetic helicity is maximal. Now the thing is here, so is maximally helical. Now if you look at the picture, so let's try to understand. Okay. So this was my vector field. In the middle it was going like that, right? So this field is exactly same as what I did in the last slide. Now its vorticity is negative, down. What about vertical velocity in the middle? Remember middle is pi pi, okay? This is 2 pi, this is 2 pi, 0, and this is also pi. So at cos pi is negative. So my vertical velocity at the center is negative, downward. So my vorticity is pointing down, and my vertical velocity also pointing down. So here there is a kinetic helicity. So this is like that helical flow. So something is going like in a circle, but it is also being pushed. So it is like corkscrew is going down. Okay. So that leads to the helical structure. So this is what this picture which I was trying to show you is exactly this. Here what happens here in this middle? It is cyclone. So the structure is like that. Yes, I plotted last time. Okay. Now what is uz here? uz 0, x is 0 and y is 0. uz is positive. So here this is going like this. So this part is contributing positive, this part is also contributing positive. So each of these places we get positive contributions for u dot omega. In fact u and omega are say equal. So this is an example where we have omega is not perpendicular to u. It is 3 component, it is not the one. For 2D of course it is true, but omega is 3 component, and if you just work it out you will find they are equal. Omega and u are in the same direction. Okay. So the example 4, I just make only one change, that my 2D fields are just change direction, change sign, sorry, change sign. So they were minus here and they were minus here before and plus in the previous example. I just change the sign. So wherever there was a cyclone will become anticyclone, right, because I change the velocity sign. So cyclones will become anticyclone and anticyclone will become cyclone. So this picture will be, so let us just draw this picture. So in the middle will be, it was anticyclone, so it becomes cyclone like that. Here it was cyclone, so it will become anticyclone. Yes, okay. What about vertical velocity? This one here, what is the vertical velocity? Positive. Vertical velocity is, I did not change the vertical velocity, I only changed ux and uy. So it is positive. vertical velocity is positive. So, my vorticity is down, my vertical velocity is up. So, what happens to u dot omega? Negative. In fact, this example omega is minus u. You can just work it out, omega is minus u. So, what happens to hk is maximally negative, because omega and u, if they are totally opposite, then u dot omega will be maximally negative. Okay. So, how much, I mean hk cannot be, for any configuration hk cannot be lower than this. Okay. So, we will do this constraint in Fourier. Fourier it becomes easy, it is not so straightforward in real space, but I will show you what is called maximal helicity. Okay. So, this cannot go lower than minus 4, and this is called maximal helical with negative sign. So, earlier example was positive sign and this negative sign. So, these are the 4 examples I will like you to keep in mind, and we will revisit them in fact several times. Okay. So, I will stop. Thank you.